Place two identical beakers side by side. One holds pure water. The other holds a highly toxic chemical. To human eyes, they are indistinguishable. When we see color in a liquid, we're actually looking at the leftovers. A beam of white light hits the surface. The liquid absorbs certain wavelengths, and the colors that bounce back into our eyes are simply the ones the liquid rejected. This chart shows the electromagnetic spectrum. Those clear liquids are interacting with light too, but their interactions happen here, in the ultraviolet band to the left of the visible range, a frequency completely invisible to human vision. To translate this invisible activity, chemists rely on an instrument called a spectrophotometer. It acts as a specialized eye designed to monitor exactly how molecular structures interact with light we cannot physically see. True chemical identification requires looking past our own senses. We have to actively measure what a substance is hiding in the dark. Inside the spectrophotometer, a specialized lamp fires a continuous, chaotic beam of light. This beam carries every single wavelength across the entire ultraviolet and visible spectrum simultaneously. Before it can be used, that chaotic beam has to be organized. The light hits a dispersion grating, or a prism, which forces the wide band of energy to split apart into its individual, pure wavelengths. Next, the light reaches a physical barrier called an exit slit. This slit blocks almost everything, allowing only one extremely narrow, monochromatic wavelength to pass through at any given moment. To successfully interrogate a molecule, the machine has to isolate a single, highly specific frequency of energy to use as a precise probe. That solitary, purified beam of light then enters a small, clear container called a cuvette, striking the target molecules floating inside the solution. Down at the quantum level, the electrons in these molecules are resting in their lowest natural orbit, known as the ground state, but they have specific, empty, higher energy orbitals hovering just above them. An electron will only absorb an incoming photon if that photon carries the exact amount of energy required to bridge the gap between those two orbitals. If the energy matches, the electron consumes the photon and makes a quantum jump to the higher level. But if the photon's energy does not perfectly match the required jump, the electron ignores it entirely, and the light passes straight through the molecule untouched. Because every distinct chemical structure has a uniquely spaced set of electron orbitals, they will only ever absorb a specific set of wavelengths. That exact pattern acts as an infallible, invisible barcode for the molecule. Zooming back out to the full cuvette, we can measure the macroscopic result of those quantum jumps. Because a certain number of photons were consumed by the molecules, the light beam exiting the container is measurably dimmer than the light that went in. This diagram illustrates that exact process. We start with the incident radiant power, labeled P0, which is the light entering the sample. By the time it exits, it has been attenuated down to the lower transmitted power, labeled P. The relationship between these values is defined by the Beer-Lambert law. It states that this drop in light intensity is directly proportional to two things: the concentration of the absorbing molecules in the liquid, and the path length or width of the container itself. The physical logic is straightforward. If you make the light travel through a wider container, or if you pack more chemical molecules into the same space, you guarantee that more light-absorbing quantum jumps will occur. By measuring the depth of this light attenuation, essentially the shadow cast by the solution, chemists use a precise mathematical formula to calculate exactly how much of a substance is floating in the sample. In the final stage, a sensitive detector catches whatever light survives the trip. The spectrophotometer then systematically repeats this entire process for every individual wavelength across the ultraviolet and visible spectrum. This graph is an absorption spectrum for vitamin A. It plots the tested wavelengths against the total amount of light absorbed. The location of the highest peak solves the qualitative mystery. Landing exactly at 324 nanometers, it definitively identifies the molecule as vitamin A. The vertical height of that same peak solves the quantitative problem. The taller the peak, the more light is missing, which tells us exactly how highly concentrated the substance is within the container. UV visible spectroscopy works by systematically probing the gaps in what we can see. By analyzing the exact dimensions of the shadows matter leaves behind, we can decode the physical world with absolute precision.